You want to evaluate this question, and this question reads: consider a continuous time LTI system described by this equation using the Fourier transform method. Of course, yes, consider this equation. Now, using the transform method, find the output y of t. So the question that you want to find, or the problem you want to find, is the expression of y of t given our input x of t is equals to exponent of minus 2t u of minus t. So the first thing is to express the equation or the differential equation given here for the system using the Fourier transform. And to do that, we just apply the Fourier transform properties that we know that when you Fourier transform the first derivative, you get j omega y of omega, and 4 of y of t becomes 4 of y of omega, and x of t becomes x of omega. That is quite straightforward. Then the next step is to bring the right terms together such that you have y on one side and x of omega on one side. This gives us j of omega plus 4 on which is multiplied by y of omega and x of omega on the other side, and therefore we can divide both sides with the x of omega to have y of omega over x of omega, and this reciprocal comes on this side, and therefore this becomes the expression for the transfer function or system response that we normally express as h of omega. So the biggest question here is to express, is to find the Fourier transform of the x of t, and so that once we find the x of t, we actually find y of omega from x of omega multiplied by h of omega. Because we have already found the h of omega, then the only item that we don't have is the x of omega, and that is obtained by finding the Fourier transform of the signal which is in time domain. This is expressed as exponent of minus 2t u of minus t. This is where the trick is. So we are going to use the Fourier transform pair that we already know, that says that that Fourier transform of exponent of minus at u of t gives us 1 over a plus j omega. Therefore, our equation is almost in that form, but it is not exactly this form because our u of t is negative u of t. So we are actually going to consider that to be to give us a hint on how we can solve that. So since we know we know this to be expressed as we know the meaning of u of t, it means that this function will be equivalent to this value for t is bigger than 0, and it will be 0 otherwise. So that is purely the meaning of u of t. If you remember, we say that u of t simply becomes 1 for anything t bigger than 0. So this being t, and therefore if it is multiplied to a function, that means our function will be having a value bigger than 0 for when t is bigger than 0. So now that we know that, now if we are given u of minus t, then the only thing that we mean is that t is actually varying. It is this sign that is varying because we are saying minus t is bigger. We are simply trying to replace u of t here with the negative, such that this becomes my minus of t is bigger than 0. So I'm just trying to change that inequality from being the way it is normally to, sorry, it is normally at t is bigger than 0. So when it becomes negative, it becomes minus negative t is bigger than 0, and therefore if you multiply both sides with negative 1, you're going to find t, the sign changes, and 0 remains as such. So this equation remains valid on the negative side of of our axis. So that is how we obtain this value, and this remains the same as it was before. And therefore, having agreed to that interpretation of u of minus t, then we can simply see that the only value that is affected by u of t is actually this value of j omega. So if it is u of t is positive, then we have a positive j omega, and if it is negative, then we have negative j omega. So if we can agree on that, then we can be able to carry on, and now we want to find the Fourier transform of our function exponent of minus 2t u of minus t. This is going to become 2 minus j omega. If this was positive, this would simply have become 2 plus j omega, but since it is now negative, it becomes 2 minus j omega, and this becomes our x of omega. And now since we have known x of omega and we had already evaluated h of omega, then as I mentioned earlier, we are going to be evaluating y of omega to be the multiplication of the two functions, h of omega multiplied by x of omega. So since we have that we can do, and we are going to be evaluate that using partial fraction expansion technique. If you're not conversant with this, you can always Google this one and you can see how it works. But I have actually showed it how it is done. So we know this, our equation is expressed as a function of two factors, this being our first factor and the second factor. It is not, this technique says that you can break up this equation, this multiplication of the two factors as two terms that are separate, like a over 4a plus j omega one factor and b over the other factor. And if that be the case, therefore this means that we can again combine this one using the method of fraction addition, of getting the common factor, or LCM, common multiple, and we evaluate for each. This becomes divided by this goes, so we are left with 2 minus j omega multiplied by a plus, if you just cancel this out with this, then you're going to be left with b multiplied by 4 plus j omega. This simply means exactly that if we were to evaluate this term in the absence of the other one, this comes back to what it was before, just like it was presented here. So that is a technique that I believe all of us should know. So having expressed our equation y of x in that format, then all we now need to do is to find the value of a. And how do we do that? We normally ignore the denominator, such that we have, this is our numerator, this is 1 times 1, which is actually the same as okay, it's supposed to be equals to this one because the denominator is the same. So if we can ignore the denominator, then we can say that 1 is equals to this one. So that is what we are doing. So there is a long method and the short method of doing that. I have just opted to use the short method, which simply says that if we have ignored the denominator and we are equating the numerators, all we need to do is to consider let the unknown term be equals to the term that we know. So what that does is that if we let this term be equals to 2, that means this more factor will give us a 0, but this do not give us a 0 for this other value. So that is how we are doing it, and we are saying that if we let j omega to be equals to 2, then our one factor that is being multiplied by a goes to 0, and the other term remains with b, and therefore we replace the j omega with the one that we use, which is 2. Becomes 4 plus 2, and therefore we say 1 equals to b plus 6, b times 6. Therefore we actually find out that b is equals to 1 over 6. Similarly, to evaluate the other one, so this is just a method that is quite straightforward. It may not appear so in the initial beginning. All we are saying is that we have this equation, which I think I can write it here so that you don't get lost. 1, drop the denominator because it is the same on both sides, and then you say is equals to a 2 minus j omega plus b 4 plus j omega. And when you do that, if you now say let this term be equals to that term, this means that this will be equals to 0, because you say we actually equating, giving j omega a value that will make this equation or this multiple come to 0. And therefore, you're going to be left with 1 equals to, and then you replace j omega with the value that we said, which is j omega is equals to 2. So you replace with the 2 there, and we have 1 is equals to b plus times 6 becomes b is equals to 1 over 6. And similarly, if we go now to eliminate b, so what we do, if we want to eliminate b, we are going to do a similar method. Equate this term to be equals to 0, which simply says that 4 plus j omega is equals to 0, and therefore j omega is equals to minus 4. And therefore, where there will be j omega, this star part, we are going to replace with minus 4. And we are going to have 1 is equals to a 2 minus 4. This becomes 6 again, and therefore we actually find this to be that case, and therefore a is equals to 1 over 6. Sorry, this is not supposed to be 1. So once we have found that to be the case, then we can express our equation replacing a, which we have found as 1 over 6, and b as 1 over 6. Therefore, we can obtain our y of t by finding the inverse Fourier transform of our y of omega, which we can now separate them as we have done. And therefore, we know that we can remember our Fourier transform pairs that we already know, that says that if you find something like 1 over a plus j omega, this is actually inverse Fourier transformed as e minus at u of t, and therefore that is how ours looks like. Therefore we can actually relate this term to this term, and therefore we can say that of course 1 over 6 is a coefficient of equation or a constant. Therefore we get 1 over 6 exponent of minus 4t u of t. The difference again comes to this one because here we have negative j omega, and if we have negative j omega, then we are going to give our negative here to u of t. That is what we have seen in our previous section. And therefore, this becomes the equation that we have been asked, because we were asked find the value or the output y of t given those terms. So that serves as our solution.